Welcome back to the Deep Dive. We're the place where we really try to get beneath the surface of the things that shape our world. And today, well, have you ever just stopped, looked up at one of those massive skyscrapers, the ones that just pierce the clouds, and wondered, how did we even do that? What pushed us to build so high, creating these incredible vertical landscapes? Well, today, we're doing a deep dive into exactly that. The amazing history of the American skyscraper. It's arguably America's most iconic architectural gift to the world. We're going to trace its journey starting from, believe it or not, the ashes of late 19th century Chicago. Then we'll follow that dramatic race for height in New York City, the early 20th century, and bring it right up to the super tall, super complex buildings we see today. Our mission, like always, is to dig into the sources, pull out the key insights, and help you understand the ambition, the tech, the economics behind these vertical cities.
And it's fascinating, isn't it? Because the skyscraper isn't just a building. It's really a dynamic reflection of, well, societal progress, how we live in cities. It's shaped by this complex mix of engineering breakthroughs, economic pressures, and even, changing social ideas about what a city should be. So throughout this deep dive, we'll explore how all these factors constantly push the limits of what everyone thought was possible. It's quite a story.
That's a great way to put it, a dynamic reflection. Okay, so where does the story kick off? You said Chicago, but not in the way people might expect. Let's unpack that. Yeah. It wasn't some grand vision from the start, was it? Came out of disaster.
Exactly. It starts with necessity, really, born from the devastation of the Great Chicago Fire in 1871. The sources give us a really powerful sense of that moment. Louis Sullivan, often called the father of the skyscraper, he wrote about it very movingly. He said, let me find the quote. Here. The Garden City had vanished with its living story. That tale could not be twice told. It had gone forever with the flames. Hence, a new story must be told. Not again would the city be the same. You see, it wasn't just about rebuilding structures. It was about rebuilding an identity, creating something entirely new from the ground up. The fire, in a way, cleared the path for innovation.
Wow. A new story must be told.
That's powerful. So the fire creates this blank slate, this opportunity. But was it just about rebuilding, or were there other forces pushing them upwards? Economics, maybe? Oh, absolutely. The timing was key. Chicago was booming, a major hub, right?
Yeah.
And after the fire, businesses rushed back to the Central Loop area. Suddenly, land there became incredibly scarce and therefore incredibly expensive. We're talking astronomical values for a plot of ground. So if you're a developer and land costs a fortune, what do? You can't really spread out.
You go up.
You go up, exactly. Maximize the usable space on that tiny, expensive footprint. So you had this perfect storm, the need to rebuild, intense demand for space, and sky-high land costs. It was the perfect incubator for the tall building.
Okay, so the pressure's there, the need is there, but wanting to build a 10 or 15-story building in the 1880s, that's one thing. How did they actually do it? Weren't buildings mostly brick and stone back then?
They were, and that was the huge limitation. Traditional load-bearing masonry walls have to get thicker and thicker at the base to support the weight above. For a really tall building, those ground floor walls would be ridiculously thick, eating up valuable space, adding immense weight. Just not practical.
Right.
So the breakthrough, the absolute game changer, was the steel skeleton.
Okay, explain that.
Instead of the walls holding up the building, you have an internal frame, a cage, really, made of steel columns and beams. That carries all the load. The sources, like Building Construction Illustrated, detail this stuff. They talk about different steel beam shapes, W shapes, S shapes, C shapes, structural tubes, each designed for specific loads. And concrete columns, too, reinforced with steel bars, designed to handle not just weight pushing down, but also side forces like wind.
Okay.
And then you have all the connections engineered just right. Steel base plates to spread the column load onto the foundation, things like backer plates where beams connect. It's intricate. This whole system meant the building was lighter, stronger, and crucially, the outside walls didn't need to hold weight anymore.
So they could be thinner, more windows.
Exactly. The walls just became a skin or cladding. That's what allowed for those larger windows that became characteristic of the Chicago school.
But the steel itself, could they trust it? Was it strong enough? Was it dangerous? I read something about that.
That's a really important point. The material science was critical. One source, Structures or Why Things Don't Fall Down, points out something fascinating. It says you could easily double the strength of basic steel by adding more carbon. Sounds great, right? Stronger steel, taller buildings.
Yeah, seems like a win.
But There's a massive trade-off. Increasing the carbon makes the steel much more brittle. It reduces what engineers call the work of fracture by like a factor of 15.
Okay, what does brittle mean in this context? Like, it snaps.
Pretty much. It means a tiny crack could suddenly become catastrophic much, much faster. The source warns that if you just doubled the strength without understanding this, a structure could be thoroughly dangerous.
Whoa.
So engineers had to be incredibly careful, balancing the need for strength with the need for the steel to have some give, some ductility, so it wouldn't fail suddenly. It was a steep learning curve.
So they were really pushing the science there. But this idea of using metal frames, it wasn't completely out of nowhere, was it? Weren't there earlier examples?
No, you're right. It wasn't invented in a vacuum. The City of Tomorrow points this out. It links this to earlier engineers, visionaries like Isambard Kingdom Brunel, Joseph Paxton with his Crystal Palace.
Ah, the Crystal Palace.
Gustav Eiffel, of course. These guys back in the mid-19th century were doing amazing things with iron and glass, building huge train sheds, bridges, the Eiffel Tower. They showed what was possible with metal structures on a grand scale.
Yeah.
So the Chicago architects, they were building on that legacy, adapting those ideas for these new commercial towers.
Okay, that makes sense. You've got the steel frame sorted, but
Right.
you mentioned Chicago's ground earlier. It was marshy, right?
Yeah.
How do you put a massive, heavy steel building on swampy land?
Yeah, that was maybe the first giant hurdle they had to clear. Chicago's soil near the lake was notoriously soft, unstable gumbo clay. A conventional foundation just wouldn't cut it for these tall, heavy structures.
So what do they do?
They pioneered the use of caisson foundations. The sources describe the open caisson method. Basically, imagine building huge wooden or steel boxes open at the bottom. They'd sink these boxes down through the mud and clay. Workers would actually go inside these open chambers at the bottom and dig out the muck by hand.
Inside the box, while it's sinking.
Yeah. As they dug, the sheer weight of the caisson structure would push it further down. They kept digging until they hit solid bedrock or a really firm layer of clay, sometimes 50, 100 feet down. Then they'd fill the box with concrete, creating a solid pier reaching all the way down to stable ground. The caisson itself became part of the permanent foundation.
That sounds incredibly dangerous and difficult.
Oh, it was. Grueling, dangerous work in cramped, wet, often pressurized conditions. But it was the only way to give these buildings the stable base they needed.
And what if they hit something unexpected, like quicksand? I read they even had a solution for that.
They did. Adaptability was key. If they hit quicksand, the sources mention using a cylindrical shell of steel, basically a big steel tube, and forcing it down through the quicksand using powerful hydraulic jacks until it reached the solid, impervious layer below.
Just forcing it through. Wow, sheer brute force and ingenuity.
Pretty much. It shows the incredible problem-solving skills and just, well, the determination of those early engineers. They were literally inventing solutions as they went.
Okay, foundation solved, steel frame up. But then there's the obvious problem. You build a 20-story marvel. How do people get to the 19th floor? Climbing stairs all day isn't exactly practical for an office building.
Exactly. The passenger elevator was the third crucial piece of the puzzle. While air sources don't detail its invention story here, its necessity is undeniable.
It had to exist for the skyscraper to work economically.
Absolutely.
Yeah.
Upper floors would be useless without it. And modern codes, like those in Building Codes Illustrated, show how central elevators are now. They're heavily regulated.
Right.
But it's not just about convenience. Safety is huge. That source talks about fire resistance ratings for exit stairs, like 2-hour ratings for taller buildings.
Right. Getting people out in an emergency.
Precisely. So vertical transport, both for everyday use with elevators and emergency egress with stairs, became fundamental to skyscraper design and regulation. The elevator unlocked the potential of all those upper floors.
So steel frame, caissons, elevators, Chicago figured out the formula, but then the action shifts, right? To New York.
Yeah, as we head into the early 20th century, the epicenter of skyscraper innovation really moves east to New York City. Well, New York already had incredible density, especially in Manhattan. Land values were possibly even higher than Chicago's, and there was this intense, well, rivalry. One source, Space, Time, and Architecture, mentions the congested Manhattan skyscrapers and suggests even figures like Le Corbusier were reacting against them in their own designs later on. So there was already a context of building tall, driven by economics, but also by this powerful desire for prestige, for corporate identity, for dominance. It was a race.
A race to the sky. And this is where we start seeing not just height, but real architectural statements, right? The famous ones.
Totally. Well, the sources don't list them all. This is the era of iconic buildings that weren't just tall, they were expressive. Think of the Woolworth Building, the Cathedral of Commerce, finished
Yeah.
in 1913.
Gothic inspired.
Yeah.
Yeah.
Hugely ornate, reaching higher than anything before it. It was a symbol. Then later you get the absolute legends, the Chrysler Building, the Empire State Building.
Ah, yes. Art Deco masterpieces.
Exactly. The Chrysler Building, completed in 1930. Stunning design. That incredible spire they secretly hoisted up to claim the height record for a while. Pure drama.
I'd heard about that. Sneaky.
And then the Empire State Building, just a year later, reclaiming the title and built at unbelievable speed. These weren't just office blocks. They were symbols of American power, ambition, even defiance during the Depression.
But all this reaching for the sky, surely there were downsides, like blocking all the sunlight from the streets. Did the city step in?
It had to. This unchecked vertical growth couldn't continue without impacting the city's livability. The streets were becoming dark canyons. So cities, especially New York, started implementing zoning laws to manage heightened density. The most famous is New York's 1916 zoning resolution.
Okay, what did that do?
It introduced the concept of setbacks. The basic idea, though the sources mention roof setback in a slightly different context, was that as a building got taller, its upper floors had to step back from the property line.
Like steps.
Exactly. Creating that characteristic wedding cake or ziggurat profile. You see on so many classic New York skyscrapers like the Empire State Building.
So the law literally shaped the buildings.
Directly. It was a compromise.
Yeah.
Allow height, but ensure some light and air could still reach the streets and lower buildings. It turned a legal restriction into a defining architectural feature of that era.
Fascinating. And were these codes really detailed?
Oh, yeah. Building Codes Illustrated shows how specific they got. There were procedures, tables, Table 504.3, 504.4,
Right.
determining allowable height in feet, number of stories, and it depended on things like what's the building used for, office, residential, and crucially, does it have sprinklers? Sprinklers might let you build a bit higher or bigger.
So safety features influenced the overall shape, too.
Definitely. It was all interconnected. Safety, especially fire safety, was a huge driver in these codes. Remember Chicago? The codes dictated fire resistance ratings for the structure, the walls. Building Codes Illustrated mentions things like the weighting could be reduced for roof structures, or fire protection wasn't needed if a roof was, say, 20 feet above the floor below. These details influenced how the tops of buildings were designed and built, constantly balancing the desire for height with the absolute need for safety.
It's interesting how these practical rules end up creating an aesthetic, but sometimes the grand plans don't quite match reality, right? You mentioned Le Corbusier.
Right. There's often a tension between these idealized architectural visions and the practicalities of city life and regulations. The Death and Life of Great American Cities offers a sharp critique of ideas like Le Corbusier's Radiant City, those towers standing alone in green parks.
Sounds nice in theory.
Yeah, but the book points out that in reality, it often just became skyscrapers and parking lots, and you could never have enough parking. It highlights how these grand visions can sometimes clash with the messy, complex reality of how cities actually function and how regulations try, sometimes imperfectly, to manage that interface.
Skyscrapers and parking lots. Okay, so moving past the Art Deco era into the mid-20th century, the look changes again, right? Dramatically. We get the glass box.
We do. A major shift. Post-war, there's this embrace of modernism, a move towards minimalism, efficiency, and often these sleek, unadorned facades dominated by glass.
What allowed them to do that? All that glass.
Technology, again. Particularly the development of the curtain wall.
Curtain wall. Sounds flimsy.
Huh, not at all. It's actually quite sophisticated. Building Construction Illustrated explains it. The key is that the exterior wall, the glass and metal grid, doesn't actually support the building's weight. It just hangs off the main structural frame, like a curtain.
Yeah, okay, it's just a skin.
Exactly. And these systems became very advanced. Metal frames with thermal breaks, little insulating barriers inside the metal to stop heat transfer. Double or triple paned insulating glass became standard for energy efficiency. They even designed clever drainage systems with weep holes to handle any moisture. Often, for high-rises, they'd install the glass from the inside using gaskets and snap-on covers. It all allows for that seemingly simple, shimmering glass facade.
But why that look? Why this simple rectangle? It seems almost boring compared to the Chrysler building.
Well, boring is one perspective, but that rectangular form had huge practical advantages. How Buildings Learn makes a great point about this. It calls rectangular buildings profoundly adaptive. Think about it. 90-degree corners are easy to work with. Easy to divide space inside, easy to arrange furniture, easy to add on to
All
later.
right, no weird angles.
Exactly. And they fit neatly onto standard city grid lots. The source says this specious old box endured precisely because it's so adaptable and functional, it just works.
Okay, function over form, maybe? So bringing us closer to today, we're seeing buildings that are not just tall, but super tall. And they're not just offices anymore, are they?
No, the game has changed again. We're in the era of super talls, yes, but also complex, mixed-use towers. Buildings that combine offices, apartments, hotels, shops, restaurants, maybe even parks or performance spaces all in one structure. Vertical cities, essentially.
How on earth do they manage that complexity, building something that massive with so many different functions?
A huge part of the answer lies in digital technology, specifically building information modeling, or BIM.
BIM. Okay, I've heard that term. What is it exactly? More than just digital blueprints.
Oh, much more. The BIM handbook and other sources call it a superior design environment. It's not just drawing. It's creating an intelligent, data-rich 3D model of the entire building.
Intelligent how?
Well, it uses 3D parametric modeling. Every element in the model, a beam, a pipe, a window, isn't just a shape. It has data attached to it.
Yeah.
It knows what it is, what it's made of, how it connects to other things. And it's parametric, meaning things are linked. If you change the size of a window, the surrounding wall opening, the structural support, even the cost estimate for the glass might automatically update.
Whoa, okay.
It drastically reduces coordination errors because the model understands the relationships between all the parts.
And they can test things with this model.
Absolutely. That's
Yeah.
a huge advantage. It's a virtual prototype. Engineers can run all sorts of analyses, structural simulations to see how it handles wind or earthquakes, energy consumption models, daylighting studies.
So you can optimize the design before you even break ground.
Precisely. Make smarter decisions earlier, when changes are less costly.
And what about avoiding those classic construction mistakes, like a duct running into a beam?
That's where clash detection comes in. This is a
Hey.
massive benefit of BIM.
Clash detection sounds dramatic.
It basically means the software automatically scans the 3D model, looking for places where different systems physically interfere, where a pipe hits a duct, or wiring conflicts with structure, and it flags them. Yep. It identifies these clashes so designers and engineers can resolve them in the digital model long before they become expensive problems on the construction site. It saves incredible amounts of time and money on rework.
That sounds incredibly useful. What else can BIM do?
Well, it integrates with scheduling. They call it 4D BIM, adding the dimension of time. You link the construction schedule activities directly to the 3D model components, so you can create an animated simulation of the entire construction sequence.
You can watch the building get built virtually.
Exactly. Step by step, phase by phase. It's amazing for planning logistics, coordinating different trades, communicating the plan, and even running what-if scenarios to optimize the schedule. And then there's 5D BIM, which adds cost.
Ah, the money.
Right. Because every element in the model have data, the system can automatically generate detailed quantity takeoffs, how much concrete, steel, glass, etc., and link that to cost databases. This means much more accurate dynamic cost estimating and budget control throughout the design and construction process.
So BIM really touches everything. Does it change how the teams work together too?
It facilitates it, definitely. It enables new approaches like integrated project delivery or IPD. With IPD, the owner, designers, main contractors, key suppliers, they all sign a single collaborative contract. They function as one integrated team.
Instead of separate silos.
Exactly. And crucially, they often share in the risks and rewards. If the project comes in under budget or performs better than expected, everyone benefits. BIM provides the shared information platform that makes this level of collaboration feasible.
It sounds like a whole new way of building.
It really is. And it ties back to that relentless drive that engineers have. There's a quote in The Existential Pleasures of Engineering that captures it perfectly. It says, "Each new achievement discloses new problems and new possibilities. The allure of these endless vistas bewitches the engineer of every era." That spirit is still driving us to build taller, smarter, more complex structures.
Ah, okay, so we've covered a lot of ground, or maybe I should say a lot of vertical space. From Chicago's rebirth through New York's race to today's digital marvels. If we try to tie it all together, what are the main threads? It feels like sheer ambition has to be number one, right? Just the human desire to build big.
Oh, absolutely. That's the spark. You see it in Individual the Power Broker. Talks about Robert Moses's almost personal drive to see his visions realized in concrete and steel. But it's also collective. The city of tomorrow highlights those abrupt technological leaps and the daring engineers who shatter limits. It's a mix of personal vision and the shared capability to achieve it.
But ambition alone isn't enough. You need the tools. So technology is the great enabler here.
Without a doubt. We've seen that progression clearly. The steel frame was foundational, then caissons conquered the ground. Elevators conquered height. More recently, curtain walls and insulating glass changed the look and performance. And now, BIM is revolutionizing the entire process. Each step unlocked new potential.
And it's a feedback loop, isn't it? Technology enables new designs, and new design ambitions push technology forward. Like Frank Lloyd Wright said, designing buildings so the machine could make them surpassingly well.
Exactly. That interplay is constant. Design adapts to technology, and technology responds to design aspirations.
And the third leg of the stool underlying everything: economics. Building skyscrapers is unbelievably expensive. There has to be a powerful financial reason.
Always. It started in Chicago with maximizing the value of that incredibly expensive land. That fundamental driver hasn't gone away. And today, with modern project management, there's intense focus on efficiency and cost control. Sources like The Goal or Project Management in Construction emphasize productivity, managing unit costs, controlling changes.
Because delays or mistakes on these mega projects cost fortunes.
Precisely. And tools like BIM are critical for that cost control, for value engineering, for keeping these incredibly complex projects on budget.
But is it just about the upfront cost anymore, or is the idea of value changing?
It is changing. It's becoming more holistic. That idea of integrated project delivery, where designers might benefit if their design leads to better construction performance or lower energy use. That points to a broader definition of value. It's not just the construction cost, the building's long-term performance, its energy efficiency, its sustainability, how well it functions for the people inside. The economic equation is getting more sophisticated.
So what an incredible journey. We've gone from the ashes of the Chicago fire through that dazzling competitive era in New York, right up to the complex, digitally designed super talls of today. It really is a story of human ambition, boosted by relentless technology and all fueled by powerful economic forces.
Absolutely. And if you step back, what you see is that the skyline, the silhouette of our cities that we often just accept as being there, it's the physical result of this constant conversation. A conversation between our aspirations to build bigger, better, higher, and the practicalities, the technologies, the economics, the regulations that make it possible. Each era learns from the last, always reaching. It's humanity shaping its environment in a really dramatic way.
That's a great way to see it. Now, Thinking in Systems has this line: the future can't be predicted, but it can be envisioned and brought lovingly into being. Systems can be designed and redesigned. So thinking about the skyscraper as this incredibly complex system, this vertical city, it makes you wonder, doesn't it? What are the next challenges? What unforeseen things, maybe climate change, maybe AI, maybe totally new ways of living or working, will shape the next leap upwards? And maybe more importantly, what values will we as a society choose to build into these structures as we aim even higher? Something for you to think about.